Hi there. All right. What I want to talk about is this slide for ultra-short pulse MPEs. This comes from the ANSI standard section 8.2.2. And what the slide says is for the retinal hazard region, 400 to 1400 nanometers, and pulses less than 100 femtoseconds, that's 1 times 10 to the minus 13 seconds, we limit the MPE to the peak irradiance allowed for a 100 femtosecond pulse. To do this, we take the MPE for 100 femtosecond pulse, and we multiply it by the ratio of our real pulse duration divided by 100 femtoseconds. So if our real laser had a pulse duration of 25 femtoseconds, we would take the MPE for 100 femtoseconds and multiply it by 25 divided by 100, or 0.25. So it would then reduce the MPE that was for a 100 femtosecond pulse to a quarter of that MPE. Outside the retinal hazard region, we do the exact same thing except for 1 nanosecond. Now, I think where people have their difficulty is saying, well, how do you get from limit the MPE to the peak irradiance allowed for a 100 femtosecond pulse to knowing to do this, ratioing the 100 femtosecond MPE by the ratio of your real pulse by 100 femtosecond pulse. Well, before we get into that, let's go take a look at the standard itself. Here's 8.2.2. It is actually on the next page, page 65, and you can read right here where it says exposure limits for pulse durations less than 100 femtoseconds are not provided for the retinal hazard region and for pulse durations less than 1 nanosecond outside the spectral hazard region because of a lack of biological data. That's the reason the table stops where it does in how short of an exposure duration it lists. It's because there's no biological data. So what they tell you is pulse durations less than 100 femtoseconds in the retinal hazard region, it is recommended, it's only a recommendation, that the peak irradiance be limited to the MPEs applicable to 100 femtoseconds, and the same for outside the retinal hazard region, except for we use 1 nanosecond. So let's now go take a look at the tables. This is for our visible. We'll see that, this is inside the retinal hazard region. So the limit of the table is 100 femtoseconds. I'm going to do the example at 700 nanometers. We'll use here, and we'll see that, it's the same MPE, 1 times 10 to the minus 7 joules per square centimeter for an exposure duration of 100 femtoseconds, and this is where the table stops. If we go outside the retinal hazard region, we'll see that the table stops at 1 nanosecond. Okay, let's go back up here, right here, to 700 nanometers. And we can see for a 100 femtosecond pulse, the MPE is 1 times 10 to the minus 7th joules per square centimeter. So from our previous discussion, if we had a 25 femtosecond pulse, we would simply multiply this by 0.25, which would make this 2.5 times 10 to the minus 8th joules per square centimeter. That would be the MPE for a 25 femtosecond pulse. Okay. Still haven't really explained how we get from peak irradiance to multiplying the MPE by this ratio. So let's take a look at the software, and we'll get started on that. So I'm going to go with 700, and since these are this duration that we're talking about is very short, so we're either talking about a single pulse laser or a laser emitting a single pulse, or we're talking about a repetitive pulse laser, but we're only talking about the single pulse. So when we're looking for the MPE, this would be for Rule 1 and Rule 1 only, short pulse duration. So we'll make this simple and just use a single pulse right now. Let me give it some energy information, and the pulse duration be 100 femtoseconds, which is 100 e to the minus 15. We'll throw in some beam information, and we get, yes, the MPE we were just looking at, 1 e to the minus 7. Now, when we say peak irradiance, let's think of it using these words, peak power irradiance. So how do we get peak power? Well, that's divide this energy, this joule, by the pulse duration. That'll give us peak power. Then we can interpret that as, that's right, picoradians, because it will be in watts per square centimeter. If we do the division of 1 e to the minus 7 divided by 1 e to the minus 13, that's 1 e to the 6th, or 1 megawatt per square centimeter of peak irradiance. So it would be 1 megawatt. That would be our limit. Okay, that's what the standard says. Limited to that peak irradiance of 1 megawatt. Now we can check our math if you'd like. And we can say 1 e to the minus, 1 e to the minus 7 divided by 1 e to the minus 13, and that equals 1 e to the 6th, or 1 megawatt. Now, let me do this. Let me go here, and I will take a quarter of this 100 femtoseconds, make it 25 femtoseconds. Okay, and sure enough, our MPE is being quartered. Okay, as I said, the software is working off this recommendation. And again, if we do the math, and you can check this with the calculator if you like, I won't do it this time. But if I divide this value, 2.5 e to the minus 8th, by 2.5 e to the minus 14, what I get is 1 e to the 6th, or 1 megawatt of peak power. So by ratioing the MPE by your real pulse duration divided by 100 femtoseconds, yes, we limit the peak irradiance to the peak irradiance of the MPE for 100 femtoseconds. Okay, if you didn't follow all that, I'm sure your instructor will be able to help clear a little bit of that up, or just watch this again and go through the math, and you'll see how we arrive at what the standard is recommending for us to do, and that is reduce the MPE by the ratio of your real pulse duration divided by 100 femtoseconds if you're in the spectral hazard region with a pulse duration of less than 100 femtoseconds, and if you're outside the retinal hazard region, you will ratio it, your real pulse, against 1 nanosecond if your real pulse is less than 1 nanosecond. Okay, that's it.